From one view, it's a very vulnerable part of the supply chain from a security perspective.
This could be as catastrophic as planes flying out of the sky, satellites giving bad, information. Imagine, GPS getting screwed up because someone tweaked a mask layer.
If you really want to do something at scale, the right place to go after that is at photomask level. You have tens of millions of features on there. And if you have one metal routing layer that's been tampered with, for example, not so easy to be able to discover that. We, for a long time, were the only U.S. supplier of so-called trusted, Cat 1A photomask, and it was viewed as a vulnerability and a real weakness in the supply chain. So another challenge you have in this kind of secure supply chain is being able to build photomasks today that look exactly like the ones we built 20 years ago.
Hey, Chris, thanks a bunch for joining us here on Micro Journeys. Great to see you here in Texas, man.
Thank you. Yeah, it's good to see you too. We've met many times, but it's the first time in my home state. So yeah, good to see you here.
Yeah, I mean, with two travel schedules, it's hard to align. Yeah. So I really appreciate you taking the time.
Sure. And you came a perfect day. It's going to hit 110 degrees out there today. So I think, you'll get a little taste of our Texas hospitality.
Oh man, if you see a guy laying on the side of the road, it's because I wore this today. Well, yeah, let's dive into this a little bit. So it sounds like born and raised in New York, right?
Yeah, New Work. My dad would work for a New York City Fire Department. He's actually a responder in 9/11. He was still working at that time, and was born in the city in the Bronx. Like a lot of families at that time, kind of started to move up further north. Westchester County, Putnam County, and settled in Putnam County. And that's kind of where I grew up. Small little lake town called Mayapack, New York. And yeah, it was a great place to grow up and meet friends and start to build my life there.
Yeah, it's it's a great area. A lot of diversity in the area, not only from a people standpoint, but there's a lot of tech influence in the state of New York, which is really exciting.
Yeah.
Is that one of the reasons that you stayed in the area for your education?
Yeah, to some degree. At that time, IBM was a big presence in all those neighborhoods north of New York, and kind of the pinnacle of achievement for a lot of kids with their parents. You got to get a job with IBM. That's what you need, because it's full employment and they have pensions and you'll never have to worry. And so, you aspire to work for IBM. That's at the time. And actually I did some summer jobs there, and it's a great company. But then, like everything, things kind of changed and imploded a little bit. And then it became, you don't want to work for IBM. And so then I started, looking for other opportunities, but always was interested in the tech business. I studied optics and engineering in college, and always knew I was going to be somewhere on the tech side of of employment.
Yeah, you were over in Rochester, right, for your undergraduate?
Yeah, but I went to school in Rochester. I went there at the time, the major was computer engineering, which was brand new. This wasn't programming. This was kind of building computers. I thought, hey, there's going to be something there. It's kind of cool. I went to the wrong advising session, actually. I went to an optics advising session, and that was the only school at the time that offered undergraduate degree in optics. And I sitting in there, what is this? And they're talking about astronomy and photography, two of my best hobbies. I'm like, this is pretty good. I can do this. And I remember calling home. My dad's like, you're going to be an optometrist. I said, no, Dad, it's nothing to do with being an optometrist. Tried to explain him what it is. He's like, so you're going to be an optometrist? I was like, all right, I'm going to stop trying. But yeah, I learned optics there. It was a great place. And I kind of fell in love with that field and still do. It's still, my passion, really, optics. I love imaging and anything to do with light propagation, all that stuff. I still stay very connected with.
You mentioned the astronomy piece. What, I guess, where's your passion in that spot?
It was mostly astrophotography. I like cameras and photos, and so I got into astrophotography. I had a pretty nice rig to be able to take pictures of, deep sky objects and near sky things. I got into image processing and that sort of stuff, stacking images, all those things that are being done today as a matter of course on a smartphone. Us amateurs had to mess around and learn how to register images, get larger exposure latitudes with stacking and focal plane variations and that sort of thing. So,
did you get into things like filter wheels and stuff like that?
Yeah. I was messing around with some of those sort of things, some custom filters. I got into solar photography for a while, and yeah, so that's where that ended. I kind of moved away from it because I just moved to places that had too much light, in the sky. So
Yeah.
that's a practical limitation of.
Well, hopefully you brought out your telescope when the eclipse happened here in
Yeah,
Texas.
yeah, we did. We got a really nice view of it here, right in North Texas. The totality, which weren't many places. Didn't have to go any further than my backyard, and honestly, it was the most awe-inspiring thing I've ever seen.
This is one area I can relate with you. So I actually flew into Dallas just for that.
Yeah,
It was it was not only mind blowing. It was one of those moments where you realize that you're in a small window of time that not many humans will ever see. Right?
Yeah, it was remarkable. And you're watching this thing kind of go across the sky, and it gets a little darker, and it's kind of cool. You see this bright ring, but when it locks in, which is not for very long, I mean, there was a lot of parties around and chat, just dead silence. Everybody was kind of in awe of this event. Yeah, so yeah, I'll never forget that. Actually, it was remarkable. Two of my friends who work for Zeiss came all the way from Germany. They're kind of eclipse chasers. They go all over the world, and we went out with them that day, and they were headed south, Texas, to try to see what's going on. I said, "You guys could stay here. We're going to have it in our backyard. No, we're going to get a good view, go down to the border and cloud it up." And they didn't really take advantage of it. So, but anyway, yeah, it was a great experience.
Yeah, I guess they'll be in Spain in what, 27, 28?
Yeah, they talked about that.
One,
they invited me to go with them. I say, yeah, that's a little more hardcore eclipse watcher than I am. If it comes over my backyard again, I'll check it out. But
yeah, kind of check this box already. I think we're good, right? So after your time over at Rochester, when did you decide to go get your PhD?
I was already been working for about 10 years, and I worked for Lincoln Labs for a while, MIT Lincoln Labs. That was my first job out of school. It was actually the so-called Star Wars, Strategic Defense Initiative contract. We were working on projects there, and I assume all this has been unclassified, but I won't say exactly what we're doing because I'm not positive. But anyway, we're bouncing lasers off of sodium layers in the atmosphere and doing adaptive optics and all that. I really liked it, but it was just about the time where those budgets were starting to get cut. There was a lot of reorgs. And I thought about getting into other imaging things there, but instead I went to work for IBM, kind of back to my hometown a little bit in northern New York. So that's where I got introduced to lithography and semiconductors and patterning in that IBM job.
Interesting.
Yeah.
So after your IBM job, when did it overlap with what you're currently doing? I guess when did you make the transition over to Photronics?
Well, let's see. I was at IBM for quite a few years. Got into the lithography stuff, and it really resonated because it was probably the most sophisticated, and I would say maybe still is, imaging application you could think of for kind of classical optics. I mean, and a lot at that time so for folks that follow lithography, now the big wavelength is EUV, 13.5 nanometers. At that time, we're working on G-line, which is one of the lines in the mercury arc lamp. And, it's, I think, 436 nanometers. So I've kind of transitioned all the way from 436 nanometer down to 13.5, which is EUV now. So the technical applications for imaging were remarkable. And I kind of fell in love with patterning and lithography and lenses at that time. Stayed with IBM for about 5 years, and then started to get interested in other applications. Went to work for Texas Instruments for a little while. Actually had my first stint to move to Texas. Then went back to IBM and thought, I really want to get a PhD in this field. I think it's important, both professionally and to do the kinds of things I want to do. It became, I don't want to say a rite of passage, but PhDs started to really become critical for a lot of people that wanted to advance their careers. So I went out with IBM support on what was called resident graduate study, which I really appreciated. They sent me to UT, started working on my PhD, and just about then IBM Microelectronics went through a lot of changes. The company itself went through a lot of changes, and most of those divisions were sold, cut. So I was a little bit out in a rowboat, in the middle of the ocean. Wasn't clear what job I was going to go back to. So I just ended up staying in Texas and went back to work for TI in that period. So that's kind of my PhD story. 10 years of employment experience, go back to school. A very, I'd say, tactical PhD. I finished the whole thing in 3.5,
Oh,
4 years. At the time I had the benefit of having been around. I had a little bit of wisdom, could not compete with the new PhD students on just sheer, memory and all those things. But I was really efficient. And so a typical degree might take 6, 7 years. I managed to get done in just about 3.5 years. So that was nice. And then I went back to work. Yeah.
that's incredible. So, since we have a spectrum of listeners, no pun intended.
Yeah.
But you describe what you mean by lithography, right? Because when people think of electronics, microelectronics, they think of companies like Texas Instruments and the fabrication process. Describe a little bit about what you mean by the lithography portion. How does that fit into this ecosystem?
Yeah. So it's the way that, integrated circuits are made. It's kind of to use an analogy, kind of a layer cake problem where there's the chips are designed, all electronic designs, kind of a blueprint for where the circuit patterns will be and how they'll operate to get some kind of electrical effect. And that's all done, in electronic design tools and things like that. So that's the blueprint for what a chip might look like. And you may need 40, 50, 60 layers, depending on the type of device, to build up all the functionality of what that fabricated chip will be. Then those blueprints go into what are called wafer fabs, where they print with giant, effectively cameras, very expensive, very sophisticated cameras. And this is where I talked about the wavelength. They print images of these device layers or circuit layers onto silicon wafers. They do some processing. Wafer comes back in, they print the next layer, and the integrated circuit is built up kind of like a layer cake. The lithography step is the part that prints the circuit pattern onto the silicon wafer. And this lithography term is kind of funny. When I worked for TI, I had we did a lot of work with Japanese suppliers, and I had my title and all that stuff translated to Japanese on the back of the card. The first time I gave my card out, Japanese, they start laughing, which is very uncharacteristic, in a particularly a Jap. I go, what's so funny? He goes, well, the translation of lithography you use means stone cutter, which is that's the Japanese word they put on your. So you're in the advanced stone cutting department. That's how we read it. But it is an old term, and that's exactly kind of where it started, and that's still the same term that's used. Now, my current company, what we make is we take those electronic design blueprints, and we make what's called a photomask. This is the master, convert those electronic design patterns into a stencil or a master that's going to go into the lithography process to print the circuit pattern. So imagine an enlarger in a darkroom for some people that still relate to that. If you don't have the negative in there, you're just printing clear light fields. Once you stick the negative in there, you get an image and you can record the image and do something with it. We make in the semiconductor or IC parlance what the negative would be. So we take the electronic design data, that's our input. We go through a manufacturing process to convert that into a physical substrate with the patterns on it, realized in materials. That goes into these lithographic scanners, these gigantic cameras, and then that's printed onto the silicon wafers to make the circuit patterns. And that's done, depending on the device, maybe 20, 30, 40 times. Those wafers come back and this structure is built up. And that's what makes at least the front end of an integrated circuit.
And so you make all shapes and sizes of masks over at Photronics. So everything from your, 2-inch wafers to your 300 millimeter wafers, right?
Yeah, that's right. So the photomasks generally are pretty standard sizes. Depending on how big the wafer is, how many times that pattern is repeated. So if you think about a circuit pattern on a photomask, that's the master. If you want to make lots of chips, you repeat, stamp that or print that on the wafer. So you might print it 100 times on a given wafer, and that's kind of called step and repeat process or step and scan process, but you're repeating that process over and over to populate a wafer. So if it's a small wafer, fewer exposures. If it's a large wafer, you get more exposures. But our substrate sizes tend to be pretty standard.
So, I'll go back to the translation here of stone cutting, right?
Yeah.
Chisel, right into
Right.
right into, some type of material, granite or something like that. Why wouldn't a company that has a fab just use a big old laser and just etch in what they want? Why have the mask and do that process?
Yeah, that's a good question, and that we would call direct writing. So that would be a technology that bypasses the mask based process, where you just direct write the wafers and the circuit patterns. I mean, the short answer, the main reason is just productivity and speed. Once you get this master photomask done and it's right, and you know it's going to print good wafers, and every circuit pattern is going to see that same mask pattern. So it really has to be perfect because you're going to produce lots of chips from it. The process is incredibly fast and productive. Like an advanced scanner can do 300-400 wafers an hour. So it's a remarkable rate of speed. And on each one of those wafers could be thousands of chips. So if you think about number of ICs per hour that can be produced in a projection printing process versus direct writing all of those, there's no comparison whatsoever. So it's productivity and cost which really drove people to using projection printing to make integrated circuits. Now, there is a place for direct writing, very, very custom chips, prototyping, any application where throughput, speed, and productivity are not some of the overriding concerns. Direct writing has a place, but it's really a niche technology even today.
So what I'm kind of hearing here is that leveraging masks in a fab minimizes a lot of the variables and increases the speed in which wafers are kind of going through the lab. With the direct write, you have, whatever the light source is, you have to control that. You have to control the stability of the wafer.
Mm-hmm. Yeah.
There's variability on a wafer to wafer basis. Plus, you're doing it in a single shot versus the other one where you're doing it, rinse and repeat, same thing over and over and over and over, right?
That's
so
right.
It minimizes the variables.
Yeah, it is an excellent point, Dan. The other thing that, electrical circuits, ICs are very sensitive to is variability, any changes. And if you're direct writing, within reason, every chip's going to be different by a reasonable amount. So controlling variability is also a lot harder. Now, with that photomask, what we make are all direct written. So nobody kind of knows that technology better than people that make photomasks. And I and our company's been involved in, consulting projects, many things with people who are trying to understand why direct writing wafers or ICs is so difficult. And it's all the subjects we covered. Variability is hard to control. It's slow. There's lots of reasons why it's been very difficult to scale it in mass production. And there's been a lot of money spent on it as well, and there continues to be. Yeah. Even around the U.S. now, there's a couple of direct writing systems that are being tested and prototyped at different places.
Interesting. So when you came on with Photronics, I'm assuming at that time it was a saturated market, lots of different companies that are kind of there. How has that landscape changed over a period of time? Yeah,
it's been big changes. And a little bit ago, you asked the question how I got into photomasks at all. Mostly because I was a wafer lithographer at IBM. So I would get the masks from the mask facility making those photomasks, we call them. And I was a user of them. And I never could, why do they take so long? Why are they not what I want? How come things aren't? And so I started to see photomask technology as a small but very critical industry in the so-called design to fab space. Most of the people making photomasks at that time, which leads to your other question, were very small. They were internal operations of chip makers. They were kind of subcritical mass. The equipment industry looked nothing like it does for ICs. The photomask industry, just to give you a sense of scale, operates about 1 to 1.5% of the IC industry. So if you got a $600 billion semiconductor industry, photomask about $6 billion, a little bit more. So it's a very small industry. And I kind of saw there, I go, this is a real bottleneck. This is the what's needed to convert designs into a wafer fab. So you don't have these things, you're printing air balls in a wafer fab. This is how designs get into the fab. And so I got interested, and the technology is quite fascinating. And so, one thing led to another, and I was recruited by, and then started to get involved in photomask making at that time. Yeah, so that's kind of how I got into it and got into direct writing and all that sort of stuff at that time. It was about 20 years ago.
And so you're saying, I mean, with this, in your example, $600 billion, $6 billion kind of difference between the fab and the photomask. One would think that there's a lot of competitors in this space. You guys have a great poster that shows, where we were and where we are. Yeah. Can you talk a little bit about that?
Yeah. So so companies like ours, Photronics, were the only kind of standalone, publicly traded photomask company. It's all we do. There's a couple regional ones. There's one in Taiwan. There's a few others. We have a few competitors that are divisions of larger companies, printing companies, but we're really the only ones that's a true global supplier, standalone. We're listed on the NASDAQ. We're the only ones that do this. And the company basically grew up out of consolidation in the industry. There are a lot of subcritical mass photomask operations owned by chip makers, regional, and little by little, Photronics, through its 50-odd year history, acquired them and integrated them into the network so we could start to get economies of scale. And so today there are a couple of players. There's still enough, but there are a smaller number of much larger players making photomasks. There's divisions inside big chip makers, like TSMC has their own internal photomask operations. Intel has their own internal photomask operations. They're called captives. And then there's a commercial photomask industry that supplies to most everybody else, and also those companies. So, you needed that critical mass and that scale to really turn this into, I would say, an industrial kind of manufacturing engine. Before that, it was, I don't know, I call it lab things, but it really was having very great difficulty scaling. So consolidation was necessary.
And so you guys are considered a merchant mask manufacturer, right?
Yeah, that's the terminology that's used. Merchant versus captive. Captive's owned by chip maker, and 95% or more of their output goes to servicing their internal fabs. Merchant mask maker, their business is selling to everybody, including companies with captives. So yeah, we're part of the merchant mask ecosystem.
And it's interesting between that, or within that ecosystem, it really sets you guys up for the way that we met. There was a period of time where there was concerns of where the pedigree of the components was coming from, or can you trust some of the different devices that you're purchasing online? Where did they originally get manufactured? So the NSA started a program called the Trusted IC program, and it was a partnership with IBM to create these components that had what was known as a trusted foundry. But after a period of time, they realized that there's more pieces to the supply chain than just a trusted foundry. Can you describe a little bit about how Photronics got involved into that space and the importance of being integrated into the trusted ecosystem for manufacturing?
Sure. Yeah, so we talked a little bit about where photomasks sit in the supply chain. So you have the electronic design, a mask is made, goes into the wafer fab, lithographic system prints the mask onto the wafers, and repeat and repeat. So the first time a electronic design is turned into a piece of physical hardware is the photomask. And so from one view, it's a very vulnerable part of the supply chain from a security perspective, because if somebody with kind of nefarious intent wanted to make a change, wanted to do anything to the design to affect something on a IC, if they make it on the photomask level, it covers every single design that's ever printed with that photomask. It's a lot easier than taking chips and repairing them locally. You can do things at scale, screw stuff up at scale if you mess around with the photomasks. So, and also it's the first time you could physically measure something. You're building a piece of hardware when you make a mask. So it's measurable, you can modify it, you can change it. So it became very much a focal point for kind of trusted or any kind of secure design flows, is we've really got to know who's building these masks, where they're stored, who has them, what kind of equipment are they being built on. because remember the lithographic scanner in the wafer fabs, it's a very sophisticated, but it's a dumb system. It's just printing what's on the mask. It would be very hard to modify a scanner to introduce some kind of ill intent in an electronic circuit. But the photomask, that's where the right place to do it. So we got a lot of attention generally as an industry. It's also an industry that's not very large. So, tend to have people get more concerned about smaller industries. There's more doors into them and there's more ways to manipulate things. So for that reason, yeah, we got involved very early in kind of the trusted foundry program. I think since maybe it's been over 10 years, we for a long time were the only U.S. supplier of so-called trusted, Cat 1A photomasks. They were certified by, at that time, it was DMEA. And we were very early in on that sort of thing. And it was viewed as a vulnerability and a real weakness in the supply chain, these photomasks. And that's kind of expanded now, the need for real security wrapped around the photomask step.
So what I think I understood you say right there is that if someone had a malicious intent, they could implement this on the mask and it would hide in plain sight. And you wouldn't be the wiser on the chip that you purchased having some kind of potential flaw, vulnerability, whatever it may be, because it would look like the family of all the other ones that you printed. And that subtlety in one mask layer on a stack of mask layers could ultimately be the demise of a particular component, a particular system. I mean, this could be as catastrophic as planes flying out of the sky. This could be as bad as satellites giving bad, information. Imagine, GPS getting screwed up because someone tweaked a mask layer in the overall supply chain. You can't do your banking anymore. Yeah. You can't find a way to get to the podcast studio. I mean, everything starts to unravel because of one little tiny nick or tweak or flaw in the mask. Do I have that right?
Yeah, I mean that's basically the idea. And if you want to do something again at scale, the right way to do it isn't take packaged chips and modify them a little with a laser system, or there's different ways you could do. You're going to impact one or two. That's fine. But if you really want to do something at scale, the right place to go after that is at photomask level. And designs can be checked. I mean, you have design databases. There's very relatively straightforward ways to check if a design's been messed around with. Is it going to work as intended? Because it's all electronic. But a photomask, if you want to really check what's on there, you have tens of millions of features on there. And if you have one metal routing layer that's been tampered with, for example, not so easy to be able to discover that. You really need 100% inspection. So, and it's a very effective way to get these sorts of things into a fab. So that's why I think it gets a lot of scrutiny from the point of view of security, vulnerability, and those sorts of attributes.
And the challenge is that it doesn't get as much visibility. And the reason I say that is that program is highlighted as the Trusted IC program, but you hear terms like a trusted foundry. You talk to people over at the Pentagon and it's, we got to work with this fab, that fab. They're making these devices. But at its core, you eliminate the masks and the security around those masks. You don't have components. Right. You don't have programs. You don't have any of these different types of things. So, I mean, I could be as bold as saying that foundationally to the program, over that course of 10 years being the only merchant mask manufacturer that was trusted, was the only way that program succeeds. Because unlike some of the other supply chain portions, right? Design ecosystem, fabrication locations, packaging, those have multiple options for end users to have. Mm-hmm. But for that 10 years, I mean, Photronics was the foundation, the only piece that if it was removed, then there is no program.
Yeah, it really would break the trust chain for sure. Yeah, I mean, I think that's a fair characterization. And we built a lot of those types of masks. And the other thing interesting is for legacy applications, DoD and things like that, a lot of those were built on very, very old technologies, quarter micron, however you want to characterize them, but they're 10, 15-year-old technologies. And a lot of our infrastructure operates on really quite dated chips. And there's nothing wrong with it. Everybody knows how they work. They're predictable. That's not a knock per se. But if, let's say, somebody wants to rebuild one of those, we want to refurb, we want to update, some guidance system, we have to keep all that equipment, all that legacy stuff running in the possibility that we might have to rebuild some of that. And that's not so easy. And, you might ask, well, just build it on new equipment in your new fabs. So I don't want to get too into the weeds here, but the other nuance with photomasks is because they're direct written, and we talked about this already, each one has its own little thumbprint. No two are really the same because you're direct writing these things, right? They're not projection printed. So if you have a legacy device, even one that's not that sophisticated from a design perspective, you really need to reproduce it exactly. And a lot of that equipment is 20, 30 years old, and some of it doesn't even run anymore. So another challenge you have in this kind of secure supply chain is being able to build photomasks today that look exactly like the ones we built 20 years ago. It's a very different kind of technical challenge than, looking at the next 2 nanometer processor for AI. It's like, no, we don't want this to look great. It's got to look exactly like it did 20 years ago. And most of those tools are gone. So how do you do that? So it's a very interesting piece of the technology for sustainable kind of legacy supply chains is capability to do this.
And one of the industries that relies on this quite heavily for that sustainment piece of processes is the U.S. government, right? And so this is a good segue into the next question. There's been quite a bit of excitement and hype about reinvesting in the domestic manufacturing ecosystem. The CHIPS initiative was the one that had most of the highlighted investment portions. The question I have for you is there was a lot of emphasis within building out fabrication capabilities. Do you think that those investments have allowed for the merchant mask capabilities to thrive? Do you think that there needs to be more investment in the mask ecosystem? How is that parallel working in tandem, since masks are so critical for the overall, manufacturing piece, not only domestically but worldwide?
Yeah, I think the way that the various programs evolved that are still kind of playing out is it was a sort of kind of trickle-down idea, which is, there's a certain amount of money we want to fund and get this U.S. chip ecosystem running. We're going to deploy the majority of it with the largest players, and then the smaller suppliers, et cetera, will benefit because those fabs and that opportunity will trickle down and they'll invest to take advantage of it. It's a reasonable way to approach it because then you don't have to pick winners and losers among a bunch of small suppliers. The concept was good. Unfortunately, particularly in photomasks in particular, since many of the largest chip makers that received funding have internal photomask operations, and even many of those masks are going to be shipped into the U.S. fabs from foreign locations, that trickle-down thing did not work so well. We would have preferred to see, okay, there's a few components if we're going to give you this money, we really need to make sure part of it gets deployed to establish a U.S.-based supply chain for those critical things like a mask, which is, as we already talked about, an extremely vulnerable and important part of semiconductor supply. You can't print a wafer with a design unless you have a mask. So that part of it, we humbly would have thought it could have been handled a little bit differently. But be that as it may, we are making some investments in the U.S. It's kind of a next region we're focused on for our company's investments. We're tracking all the fab projects, and we're kind of doing what we can to make sure there's a reliable commercial supply in the States for these masks. The toughest one is the most advanced mask. We talked about wafer lithography, and I was throwing out wavelengths earlier. So the most advanced wafer printing technology now is EUV, extreme ultraviolet, very, very short wavelengths, lets you make very, very fine features on the wafer to make advanced chips like NVIDIA's GPUs and very, very sophisticated devices. That's a very, very heavy lift to be able to fund an EUV photomask line in the US. And so under current circumstances, it's conceivable that there could be no commercial supplier of EUV masks in the States, which means all the applications will be 100% dependent on internally built captive masks. You might say, yeah, that's okay. They've been doing it and they do it for their other customers. But you got to accept the fact that a significant portion of those will be imported. They're going to be coming from overseas. You won't have a capability in the States where you can even audit designs. You send a secure design into chip maker A, and even if they built the mask themselves, one thing we've advocated is, you should pull them out of the fab every year and do a secure review and inspection of the pattern content on that. Make sure it's what you think it is and where it started. Just a simple auditing. If we can't find our way to get to this EUV capability as a commercial mask maker, these are the kinds of things that infrastructure just won't have.
Well, and that's an interesting piece. I mean, before we kicked off the podcast, we talked about, some of the tensions around the world, right? One of the major semiconductor manufacturers in the world is TSMC, right? Mm-hmm. I have to assume that their captive mask capability is in Taiwan. Mm-hmm. And if there was some kind of impact to either the exports of those masks or a earthquake, a tsunami, whatever might impact the mass manufacturing, any investment here in the United States would be all for nothing because they wouldn't have masks qualified on their processes. So, I mean, it seems like a pretty big risk for the United States to put so much money domestically without having some kind of contingency plan on a critical piece that is required during the fabrication process. Am I tracking this?
Yeah, no, that's correct. Now, companies of TSMC's scale, what they can do, maybe are doing, is they can build a captive in the U.S. next to their fabs in Arizona. They can build their masks in the States to kind of establish that sort of supply chain, which is fine. I mean, I think that's probably makes a lot of sense in their case, because you also wouldn't want to be wholly dependent on a small commercial mask maker to feed all of TSMC's fabs. And you wouldn't but still for continuity of supply and all of these things, that's not going to be the same scale and depth as their operations overseas. You'd want to have some partnered thing with a local supplier. To me, it makes sense.
Well, I mean, I'm thinking about this from a cash perspective. I mean, why would you make such a large investment as something for the potential of a catastrophe when you don't know when it's going to happen, where it's a lower cost and lower risk to just have someone that's also qualified, right? In that scenario where, I mean, you can't really predict an earthquake, right? You can't predict if there's going to be a sudden blockade or something, and then it's too late, right? Yep. So it's the beauty of being a merchant mass manufacturer. You can adapt to any of the world's environments so long as you're qualified.
Yeah. And we've, I certainly myself made this argument that, if you look at, say, 100% of the EUV masks that are forecasted to be rattling around in the US and by 2028, even if, the largest chip makers are willing to seriously pursue, we call it outsourcing, 5% of those, it is a large enough market that alone would be sufficient where we could easily justify the investment. So, don't have to say, we got to send these guys 50% of our output just to maintain continuity. Like a 5% outsourcing number is sufficient. So it is not that difficult a problem to solve, in my opinion, but we'll see. We'll see how the market evolves.
With all of the requirements from the CHIPS initiative, I mean, you had to have daycares, you had to have green energy solutions. Yeah. I'm shocked as someone that monitors this space quite a bit that they didn't have you must have 5% of your, product go through a US owned merchant mask manufacturing location. I mean, that would have been transformational, not only for the United States, the economies that are local to, Photronics and the such, but also for that security standpoint that we were talking about earlier with trust. I mean, 5% is really not much.
Yeah, it's not really much. And, the assumption was probably trickle down would kind of have that happen naturally, but photomasks are kind of a unique piece of this. And I would say, always in hindsight, it could have used a little stronger arm there. This isn't, meant self-serving for my company. I'm just simply looking at what the risks are in the current IC ecosystem, because there's a huge amount of attention on building lots of fabs. There's a lot of fabs, particularly during COVID time when supply chains were getting realigned, that sat empty because they couldn't get photomasks.
Yep.
This is our turn times in Asia went from, photomask can be 7 days, 14 days, went to 4 or 5 or 6 months during COVID to get a single mask. That means there is no way for being printed, that design.
Well, I mean, kind of following that narrative, you could have the largest solar field in the world powering your fab, but you have zero product coming out if you don't have masks.
Right.
So I can understand, the wishes that the CHIPS initiative had in adding some of these different pieces, but the reality is that you can pump in $53 billion of funds, but if you have nothing to show for it from a finished product perspective, then what was the money for? So a contingency plan like this would have, I think, benefited a lot of the different investments that came in. So we talked a little bit about, where we are as a community for microelectronics, especially in the lithography space. EUV is, where we're at right now with the cutting edge of lithography. Where do you see the future of lithography going? And how do you think that, Photronics is going to keep up with that future?
So, EUV has a couple more evolutions. There's they call it high NA EUV. And, without getting into the details there, it's kind of the next generation that allows the EUV wavelength to print even smaller features. So there's high NA lithography. There's maybe two of those tools installed right now around the world. I think Intel has one.
Pushing the limits of physics is where you're at here. Now you're getting the most possible. I mean, you're squeezing blood out of a turnip here, right? Yep. I mean, that's what you're doing with this.
Yeah, a lot of things, even the device physics start to break down when you go much smaller than that. And the economics start to really kind of turn upside down. You're talking about, single high NA EUV scanners. I won't give the numbers, but people can find them. They're staggering amounts of numbers. So staggering numbers. So the number of users that can benefit from that sort of technology, very small. You're talking extremely high runner, high margin chips. That they're the only ones really who are going to be able to productively deploy these kind of patterning technologies and make any money, which is, in the end, it has to be sustainable. Somebody has to make money. So, we're following that. We're setting the table for current high NA today. We've got about 50% of that in order. We are going to chip away and get our best to get an EUV commercial line in the States. And then high NA will start on that next. Maybe when there's 8 to 10 tools installed, it starts to pressurize a business that we can look at. But the piece of it and the role we see playing in the evolution of semiconductors is more that mid-range. EUV and high NA EUV only right for a couple of chip makers, NVIDIA, and really high volume, very, very advanced designs. There's an enormous amount of IC design activity at these mid-range nodes, and even some of the less sophisticated nodes for EUV. And the problem is the low runner model in semiconductor today is totally broken. The cost it takes to get a design, get mass built, get it into the fab, and get yield, do what are called respins, make the thing function right, do that process over 2 or 3 times, and then ramp production, is really not accessible to a lot of companies anymore. So we kind of see one of our roles is to lower the barrier of entry in these somewhat advanced nodes. So more designs, it's this lab to fab stuff, more designs that are sitting on shelves can get into fabs, get prototypes done, get respins done and tuned, and have a chance to either be shipped in low volume or high volume. So most of the technology development we have right now is geared towards making prototyping faster, cheaper, more secure, lowering the barrier of entry, getting more assurance of yield, first pass yield on new designs. We see that as the biggest, one of the biggest gaps in the industry today.
So let me reinterpret this. Sounds like state of the practice. What is, kind of not, it was yesterday's state of the art is your focal point. You see a peak there in where not only opportunity space is, but also demand. And within those two, buying or reducing the cost and the barriers to entry is a core focus. Is that correct?
Yeah, I mean that's basically the idea. And the what's called the so ASICs, application specific integrated circuits, ASIC versus programmable devices, and even GPUs like NVIDIA makes. ASICs are different. They're a chip that's designed to do a specific thing, run a washing machine or answer your phone, whatever it is. It's the design itself that carries most of the functionality. And so it's very design driven. So each ASIC needs a new design. The associated chips need new designs. And so we are seeing, the kind of a resurgence in, I don't want to use the word golden age, but a real pent up demand to use ASICs or chip design as a way for companies to differentiate and do more cost effective functionality. Because programmable chips, they have power issues. They tend to cost more per function. So if you can custom design a chip to do something, generally it's going to be a better solution.
Well, it kind of goes to our earlier comment, which was variables, right? With an ASIC, you minimize and eliminate a lot of the variables. It has one task, and it does it extremely well. Something that is programmable, like a field programmable gate array, an FPGA, has a ton of variables. Now you have, everything from fuses going off within there. You have programs that you have to upload. And each of these different steps causes potential issues with performance, whether it be power performance, just applicability, integration. All these different types of pieces are impacted. So I can see why ASICs would be, a very sought after piece, because this is the way that much of the industry is going, with things that are heavily focused on, one type of application, just getting it done really well, right? Yep. So
and you look at all big players, Microsoft, Apple, all these companies are designing their own ASICs now. You can just search cloud ASIC, and you will see not just an Intel processor, an AMD processor, or GPUs. You see range of custom designs that are being knitted together with these very high performance processors to do certain functions. Edge devices, there's a lot of custom ASICs to do localized, AI inferencing on the edge. So differentiation by design and getting that design engine really working is key. You have a problem you want to solve, well, we can try to design a chip to do it, but you can't spend $100 million in 10 years to get a first prototype out. So that whole thing has got to be more accessible, streamlined. Prototyping and getting feedback in the fabs has to be done readily. And the very large foundries, like, if you're a TSMC salesperson and somebody says, I want to prototype 10 chips of a new design, you're not going to return their call. I'm not being a knock on TSMC, but I mean,
why would they care, right?
Well, that mask set alone is going to cost you $6 million. So do you really want to prototype this design? So anyway, so where we see our role on mask units globally, this isn't revenue, units globally, we're probably number one. We may produce 35% of all mask units in the world. A lot of them are for low-end legacy applications. So we're kind of right at the tip of the spear, if you will, of this problem of a really clogged up prototyping line, getting ideas from chip onto electronic design, getting mass built, and getting protos built in a fab. So we see a very, very important role we think we can play there. And there we're a big player. We produce, a third of the units, photomask units globally. So our masks touch, almost any design fabric you can think of. Somewhere they're kind of touched by one of our masks. So
I bet you somewhere in this room, there's probably, hundreds of components that are touched by Photronics.
It's absolutely true. So this is an area. So we want to, obviously it's, this is a business. So we want to try to, I don't use the word exploit. That doesn't sound right. We want to leverage that breadth. And then also we've identified this problem, which we're not the only ones. to see that we've really got to improve productivity and speed. And then EUV, here, this is my opinion. If EUV is going to be a long-term 10-year solution for the industry, it has to broaden its user base. You can't have 3 or 4 customers. It needs to be accessible to more users. So,
and that's because the tools right now are just so expensive to operate, to purchase, and then one of the biggest challenges is the personnel. There's only a few people that are trained to use those tools.
That's right.
So you couple those 3 things together, and it's no wonder that there's only a few customers, because this is the only ones that can afford it.
That's right. Yeah.
Right.
So if you look at like this NatCast center that was funded in New York, they call the EUV Accelerator. And, you read a little bit about at least what their vision is. They kind of identify this, lab to fab. We want to make this more accessible. We want to improve the prototyping flows. So obviously want to make our presence known to that community, because we understand how to do that part of the supply chain. That's kind of our bread and butter. So that's where we want to play. And we have a lot of R&D programs geared towards that part of it.
Yeah, hopefully it isn't siloed from those that have been working in this space for quite some time.
I hope not.
It would be good to ensure that taxpayer dollars are getting maximized by the best and the brightest in this particular field. So that way it does lower cost, from tool sets to trained personnel to all of the different factors we talked about. And I think that this adds yet another extension to what you were describing about the future of Photronics, hitting that state of the practice piece, but also looking at the horizon. Hey, we know that this is something that is integrated in today, and we want to make this available for the masses. So that way, good ideas continue to get printed out in ASIC form or whatever they may be. And there is an opportunity here for Photronics to buy down that risk. Yeah,
that's the idea. And, people are liking this word democratization of design and of this. So we could tag masks onto the back of that, understanding they can be a bottleneck. They're slow. They can be expensive, but that's kind of our focus. And I kind of grew up, and even when I did my dissertation, I'm a computation person, mostly because I tried to do everything I could not to have to go in the fab. So I learned a lot about modeling and simulation and all these sorts of things. And our customers, the design people and the wafer people, kind of embraced heavy duty computation to make their lines more productive and improve yield risks. Photomask people way behind on that. So they say, well, how are you going to do this? You still need to make money off these things, and they take X amount of time to build. I think the next phase of evolution in the mask industry is to really get computation, high performance computing, all of those things into the mask infrastructure, which is not the case today. I mean, I would like to see a full digital twin of our, a mask making line from design to a predicted wafer output available in a cloud environment that somebody could kind of virtually prototype and test a new design. You think, yeah, why not? But that's actually not, it's a difficult problem. And, but just that alone would have a tremendous leverage value to increase speed, which wouldn't waste as much time in hardware. So that's, you said, what areas are you emphasizing? Of course, yield and productivity, but getting computation seriously and modeling into the design flow for masks is really the key.
Let me pull that thread a little bit, because this is interesting. What you're describing here is an ability with this digital twin ecosystem as a future, opportunity for investment, whether it come from the U.S. government, whether it come from another source, who knows. But in this space, now the users have the ability to try a bunch of stuff digitally without having to pay the high price tag for prototyping. Did I get that right?
Yeah, I mean, it's a virtual prototyping flow, which exists in pockets already. People can get a pretty good idea what might happen if you print a device pattern on a wafer, what the yield might be. The EDA, or design automation people, are very good at this. They do timing models and all kinds of things where they can predict what might happen.
Yeah, they've made whole businesses on this.
Right, whole businesses on it. The mask community, because it's small and other reasons, and some of it is a little hard to model for various reasons, it's has not, stepped up in this particular way to connect those two pieces. And that really is, I think, could have a very large impact on all these things we've been talking about: lowering cost, improving cycle time, getting more assurance of first-time yield. So we want to, the mask sits there. It's on the perch between these two things. And you have two groups that are pretty sophisticated with this stuff already. We want to, work to fill in that gap.
Yeah, this sounds almost like a DARPA program in the making here. Something that helps workforce, helps lower cost, helps with sustainment, critical piece to the Defense Department. I mean, sounds like an interesting area to explore, here in the future. But Chris, this was great having you here on the podcast, and looking forward to many of the more ideas and continuing our friendship down the road.
Yeah, thank you for the invitation, Dan. Yeah, I really appreciate it.